This lecture will be going over techniques for data cleansing. Most of this lecture will follow closely the article by Mueller and Freitag, Problems, Methods, and Challenges in Data Cleansing. If you have not read that, pause, go read that paper, and come back. This lecture will go over three primary topics: the topic of data cleansing, defining it, a description of anomalies that can happen in your data, and a description of data quality criterion that can be impacted by these anomalies. First, let's introduce the concept of data cleansing. Often, students and early scientists neglect thinking carefully about sources of error in their data itself. Even if you have a tidy, organized data table, there can be problems or anomalies in your data that can introduce systemic errors in your analyses and your outcomes. And data cleansing, or auditing and checking your data for these errors, is a systematic way of defining what the errors are, accounting for them, and cleaning your data table so that your analysis, which remember is supposed to reveal patterns about the world through your data, is clean. Many types of errors in your data can actually cause spurious outcomes, whether false positives or false negatives, that have detrimental impact to our understanding of the story behind your data. Real data is really messy. Even if you have a tidy data table, there are lots of ways that errors can be present. Some are obvious, you can see them right away. Some are hidden. Some are require careful vetting of your data table. Data cleansing is the process of identifying and accounting for anomalies in your data, particularly your data table itself. Remember, the assumption is that the evidence that you have in hand, your observations, have a veridical mapping to entities or things in the real world. So there's some real world out there that produced the quantifiable measurements that you've collected that leads to these observations, and that the observations have a tight mapping to things in the real world. Any kind of interference in this mapping from errors, systemic errors in data types, data entries, things like that, break this mapping. So data cleansing is carefully understanding this mapping between the things you're trying to measure and the actual table of observations that you have that you'll use for inferring structure in the environment. Before we go into the process of data cleansing, however, it's important to kind of be on the same page with regards to terms that we'll be using in this lecture. When we refer to anomaly, we're referring to a property of data that renders it an incorrect representation of the world. Anomaly is a general use term for an error in your data table. Data, we'll talk as being a symbolic representation of information. This is consistent with other definitions that have been used in other lectures of this course. A tuple is a list of discrete values from a finite set. It's basically just a set of values. And a feature vector is a collection of observations, in the same way that we talked about a variable last time. So a column of your data table is a feature vector. You can think of feature vector and variable as being synonymous. With that in mind, let's go over the types of anomalies that can typically happen in your data sets. And these are the classes of anomalies that were proposed by Mueller and Freiberg. First, there are syntactical anomalies. These are errors in labels or formats. Next, we'll go over semantic anomalies, which are errors in the fundamental value of observations themselves. And finally, there are coverage anomalies. These are gaps in the collection process. Let's consider the different types of anomalies in turn. First, let's think about syntactical anomalies. There are many different subtypes of syntactical anomalies. The first one that we go over are lexical errors. These are discrepancies between the structure of data and the format. So if you look at the table here on the right, in the reaction type column, there's actually an incorrect positioning of a trial from the accuracy column sitting in the RT column. So the structure of the RT column is supposed to be reaction times, but there is a incorrect placement of a non-RT measure, in this case your accuracy measure on that trial, put in that column. These often happen when you're trying to parse and restructure data tables and you incorrectly do so. Although sometimes these can be different types of errors from just spitting the output out from your experimental code. Next, there are domain format errors. These are errors in the value for an attribute not matching the domain. What do I mean by that? Well, take a look at this data table on the right and look at the column for the name of the participant. First you have Smith, John, then you have Doe, Jane, then you have Smith, Karen, and then you have Payne, Max. So here, there's a missing comma that defines the last comma first name format structure that had been used in that variable before. So that one entry violates the domain attribute of the last comma first name that was used for that variable. And if you have, let's say, a routine that's meant to pull this variable from this data table and, let's say, present something in a PDF or whatnot, it will have trouble parsing the first and last names because usually they'll look for commas. This isn't the only domain format error, it's just an example. Next, you can have irregularities, which are non-uniform use of values, units, or observations. So, for example, if we go back to this data table on the right where we have subject ID, trial number, condition, and let's say average reaction time in that condition, you'll notice that we have reaction times mostly done in milliseconds, but there's this odd value down here, which happens as a result of erroneously reporting the response speed in seconds instead of milliseconds, which was the traditional domain format. This can often happen if you have multiple human users entering data by hand and certain data types have different units that are used. So for example, seconds versus milliseconds. You'll also see this when you are using, let's say, accuracy as being correct or incorrect and it accidentally gets replaced with an I or a C or a 0 and a 1. These irregularities happen quite a bit with human manual entry into data tables, but it can also happen from other types of errors if you have automated data collection and writing tools like a PsychoPy or ePrime script that collects your data. So syntactical errors are all really related to just a misprint of something that was supposed to be a clear value. So they're just the syntax of how an observation or a value was put into the data table was wrong. Semantic anomalies, on the other hand, have to do with changes or breakdowns in the actual meaning of the values themselves. So for example, integrity constraint violations are cases where the value does not match the constraints of that attribute itself. Take a look at this data table on the right where you have subject ID, age, and date of birth. In the age column, you have an age that's a negative value, and this -1 here. Now, we know that that age has to be constrained to greater than 0. And so negative values for age do not make sense, at least just chronological age. Differences in age might be another story, but the assumption is here that age in years cannot be negative. And so this value violates that constraint of the attribute of age. You'll also see that with, say, like negative reaction times. There's no such thing as a negative reaction time in its traditional form. So that will violate the meaning or the way you interpret that value. Contradictions are cases where values violate a particular dependency. So for example, here in this data table where we have subject ID, age, and date of birth again, you'll notice that in the last row for subject 4, the age, 68 years, doesn't match the date of birth, assuming that this data was collected in 2020. Somebody born in 1991 cannot be 68 in the year 2020 or 2021. So clearly the assumed mapping between these two variables is violated. Now you wouldn't clearly see this in the same way as an integrity constraint violation that I showed you before. A lot of this involves knowing in a deeper way relations between your variables. There are also duplicate errors where you have 2 or more data points representing the same thing. This can happen when you have a duplicate subject actually given 2 different ID numbers, or where the same data file is parsed twice. So for example, here in this data table where we again have subject ID, age, and date of birth, you'll notice that there are 2 subjects, subject 3 and subject 4, who both have an age of 37 years and the exact same birth date, 1/1/1984. It is very unlikely for 2 subjects to have duplicate date of births. It's possible, but statistically unlikely with small sample sizes. So in this case, this would be flagged as a potential duplicate error. You might have actually had the same participant twice. The duplicates really mostly consist of duplicates across rows, but you can see duplicates across columns as well. And finally, there are invalid tuples, which is just a general case for all the other semantic errors. Semantic errors are complicated, so there are many ways in which the mapping between the meaning of an entry and its representation for an underlying variable can be broken. And so invalid tuples are just the general case for that. So for example, in this data table again, where we have subject ID, age, and date of birth, you might have an entry of somebody who was born supposedly in 1891 and would be 128 years old today. This is an extreme outlier value. It's very unlikely for you to have someone in your data set that is 128 years old. This, again, is one of those cases where you have to understand the nature of the data that you're collecting. You have to understand what the average distribution of age is and what can or can't be an outlier likely. So this would be a case of an invalid tuple. This date of birth and age are likely to be a calculation error or a manual entry error. Finally, coverage anomalies are cases where you kind of parsed or covered the actual range of data incorrectly. Now, one of the most common things you'll see are missing values. These are the omission of an observation or a data point. If we take this data table here on the right, you'll notice that we have a missing or gap entry for subject 3 where no age is entered. We have their date of birth, but we do not have their age. These are pretty quick and easy to see. Now, in a lot of cases, if you're working with data tables that you don't visually parse through or scan through and look at them, these missing values can cause problems because you might have a tidy data table transformation, or you're trying to kind of reshape these data tables, and this will be seen as just an empty gap. And often this will lead to parsing errors and whatnot in your data tables. Missing tuples, as opposed to missing values, are just the omission of a full variable or feature vector. So this is the case where you're expecting to see date of birth, but again, there is no entry for any subject in any of the observations for the date of birth column. This is pretty easy to detect because an entire column will be missing. Now, missing values and missing tuples are the two big coverage errors that you'll see, and they're pretty quick to see. In many cases, in R and MATLAB and Python, if you actually have missing values or partially observed variables, there are entries that you specifically designate to indicate that something is missing. Nans, or not a number, are a common way of referring to an omitted observation or value. And this just flags in your data table that you know there's something that's supposed to be there, and you have no way of actually getting that information. That's different than these coverage errors, where coverage errors are you assume that there should be an entry, but there's not. Now, why is it important to have a hierarchy or taxonomy of anomalies? Well, each class and type of anomaly will have a different impact on the quality of your data itself. But specifically, it'll impact that mapping between the real world and your observations in very particular ways. So remember, our assumption here is that your observations, your data, have some direct isomorphism to things in the real world, and that you have a clean mapping between your observations and the thing you're trying to understand in the real world. And these anomalies distort that mapping. They introduce noise, so they introduce transformations in that mapping. And as a result, these specific types of changes caused by specific anomalies will have very specific disruptions of this mapping. So essentially what you want to do is understand how anomalies distort this mapping between the world and the observations, and understanding that will allow for you to think about how to build data cleansing routines in order to fix and clean and make your data an accurate table with which to do your analyses. Now, Mueller and Freytag came up with a set of data quality criterion in order to think about exactly how to evaluate the quality of your data. They break them down into two large domains. And the first domain is accuracy criteria. And these are just measures of the exact, uniform, and complete representations of the world in your data. Under accuracy, you can have things like integrity criteria, determining whether or not the dataset contains representations of all the desired aspects of the world. So these are impacted largely by semantic anomalies. Integrity type criteria can include completeness, which is a measure of the uniqueness of variables and observations that are present. You can also have validity, which measures whether or not you have contradictions or invalid tuples. Another subdomain of accuracy is consistency evaluations or consistency criteria. These are criteria that determine whether or not your data set is uniform and free of contradictions. These reflect, or these types of quality are impacted by syntactical anomalies. So whether or not you have schema conformity, do you have lexical or domain formatting errors, uniformity, or all the observations of the same variable in the same format. You can also have accuracy impact quality of the density of your data. And by density, really what we just mean is that if you have n observations and p variables, you should have exactly n by p values. And these reflect or are impacted by coverage anomalies. So essentially, if you should have an entry for every cell in your data table. If you have n observations and n rows and p columns, you should have n times p entries of cells in your data table. Now, the second broad class of data quality criterion, which is just into its own, is uniqueness. And this is just a measure of whether or not you have duplicate entries or variables. Now, there's a specific mapping between anomalies and criterion, and some anomalies can indirectly impact criterion or have direct impact on criterions. So every anomaly at least has a single direct impact on one type of data quality criterion. but some of them can indirectly influence other criterion through their impact on another criterion. So for example, lexical errors directly impact the schema conformity criteria. But as a result of reducing quality in schema conformity, you also can have consequences in validity, uniformity, density, and uniqueness. Domain format errors, on the other hand, will also impact schema conformity, but will only indirectly impact validity, uniformity, and uniqueness. They don't impact density itself because you still have observations there. Irregularities hit uniformity directly and indirectly influence validity and uniqueness criteria. Constraint violations will only impact validity directly. Missing values will impact the density as well as the uniqueness of your data. Missing tuples, on the other hand, only directly impact completeness. Duplicates will only impact uniqueness, and invalid tuples will only impact validity. So you see there's this complex relationship between each data quality criterion and each anomaly. And you really want to take to heart understanding this relationship, because the goal is to understand how to search for these anomalies, correct for them, in order to have your data be as high quality as it can be before you start your investigations. And Mueller and Freytag propose a philosophy for how to do or build data cleansing pipelines. Everything I'm going to be talking about in terms of data quality pipelines, you can do and you should be doing as automated pipelines. However, there are some cases where you might need to do certain steps manually. Preferably, if you can do it in an automated fashion, do it in an automated fashion. There are lots of beautiful tools in R and Python and some in MATLAB for doing these. If it's unavoidable and you need to have human-induced checks on this, you should just be systematic. But whether or not you're doing an automated pipeline or a manual pipeline, you want to think of the process as following a particular set of stages. So first you want to start with data auditing. What you want to do is you want to take a subsample of observations and check for anomalies. Just a random subset. If you have 10,000 rows because you have a large data set of 10,000 participants, take a random 100 rows and look at or evaluate those rows across all variables you have and look for anomalies. With that data that you've subset, you're auditing out, you want to determine a workflow specification, which is how to automatically detect and deal with anomalies. Are you looking for cells with no entries? Are you making sure that the values in a particular column fall within a particular range? Are you making sure that if they're a string that they have commas in the appropriate places? Now, to set up your workflow specification, you want to have a detection and resolution pipeline in place. So you want scripts that classify consistency in the data to find anomalies, and resolutions in terms of algorithms or logics for how to deal with those anomalies. The workflow specification itself is the art of data cleansing. Once you've set up that workflow where you detect anomalies and you figure out tools for resolving them, for example, detect missing observations or missing values in a single observation for a particular variable, and replace that empty value with NaN or Na to indicate that there's not a number there. Or if you have an age that seems to be in months instead of years, figuring out how to do the calculation to project it into years, etc. Once you have that workflow, you simply have to execute it. So you've audited your data set, you've figured out what anomalies you're trying to look for in your data, because not all anomalies will be present in all data. Once you flag the type of anomalies that you see in your audited set, you develop your workflow. Now you apply your workflow to the entire data set. So this is applying your routines of detection and resolution on the entire data table. And then you want to set up a post-processing review. You want to recheck your data and see whether or not you accurately accounted for those anomalies. So take that same audited sample where you've detected your anomalies, confirm that the anomalies are removed in that subset, and then you repeat the process over again. You audit another sample of your data, and you see if you can find any anomalies in that audited subset. If you don't see any anomalies in that audited subset, stop. If you do see anomalies, new anomalies, develop a workflow for fixing that, or modify your current workflow to include those anomalies. Implement it, review, do it again. So the idea is that you're going to keep doing this audited check and workflow specification for handling anomalies in your data set until what you have left is a very clean data set that lacks anomalies that impact that mapping between assumptions of the real world and your data set itself. So this pipeline logic really just defines the logic for cleansing pipelines. This is a set of principles for how you should build your pipelines in your data set. And a key thing here is you should be leaving your original data untouched. So you can have your original data table. You make a copy of your data table, which is the one that gets cleaned and audited and readjusted. And you can work with the clean data table. Now, if anything happens, you realize that one of your auditing or your resolution steps was incorrect, you can always go back to the original data set that has all those errors and has all those anomalies, but now you know what to look for and how to fix them. So leaving the original data untouched and working with a separate file that's clean or a separate table that's clean gives you lots of flexibility for going back and forth and continually fixing these errors as they come up. With very large, complex data sets, this is a constant process and will involve lots of steps of going back to the original data. Most importantly, automate as many steps as possible. Like I said, not all steps will be possible for automated logics, but many will, and especially since most of your data analysis is being done in a statistical programming language of some sort, you can specify a lot of routines for doing these searches. And you want to have it so that you have a pipeline that goes from your raw, dirty data table to a clean version of your data table. And you can hand somebody your pipeline and your dirty data table, and they can independently generate your clean data table. That's the fundamental goal. Again, this makes it so that you're open about how you're cleaning your data. People can see the logic, can see the routines you did to clean your data. That's the most important part. When you can't, when you have to have some manual judgment, document. And if you can, have inter-raters. So have multiple people audit the same thing and come to a consensus before changing. These are the fundamental steps of data cleansing. And you can see how now, in order to implement data cleansing, you have to have a really good understanding as to what you're looking for. What are the types of anomalies you're looking for? What are the ways those anomalies can impact your data, and how can those be expressed? Once you have that understanding, generating methods for cleansing your data start to make a lot more sense. So if you take anything away from this lecture, I hope you can see that developing a formal process for identifying anomalies, correcting identified anomalies, and evaluating for quality makes your data a more veridical representation of the real world. Remember, the goal is to understand the story of the real world that your data is telling you, the story behind your data. Every time your data gets distorted with errors and anomalies, you lose or distance yourself from the real story behind your data. So data cleansing should be a critical part of your pre-steps before understanding and doing an investigation of your data. This should all be a standardized pre-processing routine, along with making sure your data tables are nice and tidy. Because when you have clean data, you'll get a clean understanding of the story it's trying to tell.